Hello everyone, my name is Neha and this is the 16th lecture on Introduction to Microcontrollers. In this lecture, we're going to see the program for rotating LED on each button press. So before I show you the program code and the flowchart for this particular program in which we are trying to rotate the LED by pressing the button, which is the switch S1 here, you can see. So before I show that, I want to give you the demonstration of this code on the development board so that you have an idea what we are trying to do in this code. So I'm going to play this video now. And you can see that I am pressing the S1 switch. And as I press the switch, the LED rotates towards left. Okay. So here I'd like to pause a little bit and want to let you know that if you see carefully, you'll get to know every time when I am not pressing the button, which means when the button is released, at that time the LED is turned on. And when I press the button, then basically at that time the rotation takes place. And every time I release from that button press, you will see the reflection, or you will see the rotation to the left to the LED on the left hand side. So, and then I want you to carefully observe one other thing in this program is that after the LED, after pressing the switch, when it leads to this LED, when this LED is turned on, which is RA7, then after that there is a lag, and after that lag this RA4 is turned on. Okay, so watch that carefully and then I'll explain you later on. So you see the LED is turning on, and then now the RA7 is turned on and there is some lag, and then RA4 is turned on. And you see every time I press the button, the rotation takes place. So here the code which I'm going to explain in this lecture is for this particular demo which you saw here, and it has a lag, and your job is to figure out how you can remove that lag. So I would recommend you to follow the program which I will be showing in this lecture. Try to run that on your MP lab, and then think about how you can remove that lag. What's instruction set you can use to avoid that lag and make all the LEDs turn on in sequence. Now let's start with the flowchart. So this is the flowchart for rotating LED with each button pressed towards left, and it starts with the read button, and you know that our button is S1 and S1 is connected to RB4 pin. Okay, so it's going to read the button, and then there is a decision box which says if RB4 is equals to 0, and then there is a question mark, is button pressed. Okay, so when your button is pressed, at that time your RB4 is basically cleared. It is basically equals to 0. Okay, so it's asking the question if RB4 is pressed or not. So if it is not pressed, which means your button is released, and I showed you in the previous slide that every time when the button is not pressed, then at that time the LED is on. Okay, so if the button is not pressed, if this statement is not equals to 0, then then your flowchart will basically flow in this direction, which means this is no. And if it goes here, then it says LED will be on. So if the button is not pressed, if the button is released, in that case LED is going to turn on. And then it says clear flag. Okay, so we are using a flag bit which is a general purpose resistor in our code, but for now just understand that flag we are just flagging it every time LED is turned on. We are clearing the flag. Okay, so we are clearing the flag every time the LED is turned on. So this is our first step. Like if the button is not pressed, if it is released, then LED will be on and this flag will be cleared, and then it will go to loop again and ask the same question. Okay, read the button. Read RB4 whether it's equals to 0 or not. Is button pressed? So let's see. In second case, the button is pressed. RB4 is equals to 0. Then it will go to this box you see here, and this box says rotate LED left. So you will be using some instruction which will help in rotating the LED towards left. Okay, and now here in this case, every time the LED rotates towards left, we are setting a flag bit. And here you saw we cleared the flag, and here we are setting it up. So remember, like when the LED is on, at that time we are clearing the flag. Okay, and every time we are rotating the LED, we are setting the flag. So this is the flag bit which we are using, and I'll tell you what it is in the code later on. But for now, understand the two case of this flag bit. Flag bit will be 0 or it will be cleared when LED is on, and LED is on when the button is released. And flag bit is set every time the LED is rotated. Okay. Now moving on here, it says RB4 is equals to 1, which means RB4 is set, and if it is set, at that time button is released. So whenever the button is released, that's the set position of your switch. Okay, so it is asking this question whether RB4 is equals to 1, is button released. So if RB4 is equals to 1, that means your LED is going to be turned on. Okay, so if it is yes, you see here LED is rotated and whatever the LED is on the left will be turned on, and then this will go to this loop, and then this loop will be continued. And what if the button is not released? What if the RB4 is not equals to 1? And if it is no, then LED will be off, because that means the button is pressed, and if the button is pressed, then the LED will be off, and this question, it's going to ask this question again. Okay, so this is my flowchart for this program, and there is no single answer to the flowchart for the particular program which we are making. So you can create the flowchart in your way, or you can use a simple algorithm step-by-step method. Any of those method works. Now I'm going to jump into the code. So here you see the full code for rotating LED with input button, and here we start with the code. This is our start code, and these are the different labels which I have used in this code. So I'm going to explain you each step and how the operation of rotating LED is performed in this program. But before we get into in deep of all these labels, I just wanted to show you the whole code. So this is your whole code, and now next we are going to see each label and what does it mean and how the code works. Okay, so starting with the flag bit and LED pattern, you see these are the two general purpose resistors which I have used, and this is their address. 0 cross 25 is the address, 25 is the hexadecimal number, and this is at this address whatever the resistor is we have used, and we have named that resistor as our flag bit. And there is another resistor which lies at 26 hexadecimal position. We have used that resistor and we have named that resistor as LED underscore pattern. And EQU are the constant directive. So these are the assembler directive. These are used to define the constant. So we are defining our register, and that's why we have used, and we have used this in the past programs also. So flag bit and LED pattern are the label for addressing general purpose register, which lies in the bank 0. So if you have any doubt, you can get in, you can see the bank 0 and see how many registers are there in bank 0. And this bank 0 you can find in the data sheet of the microprocessor which you are using. And in that you can see at these address they are general purpose registers, and you can use whatever the name you want. I have used flag underscore bit and LED underscore pattern for my program. So bank 0 at the specified address above, these two general purpose register will be used in the program. Okay, so now moving on to the main program code. So this is the starting of the code. Okay, so starting with bank cell and cell B, you know that if we want to provide any input, we use this N cell B. So bank cell N cell B, and then clear F N cell B, and you know that this N cell B, it lies in the bank 0. Okay, so we are using sorry, bank 30, it lies in the bank 30, and we are using this to define the input. Okay, so N cell B, bank cells, using the bank cell we have selected N cell B, and we are clearing all the bits of N cell B, and making this port B as a digital input. So I should have written here as digital input. So but I have covered this portion already in the last lecture, so I hope you already know that if you clear all the bits of NCLP, then your port will be act as a digital input. And then again bank cell select port A. So we have to do 2 times bank select because this lies in the bank 30, and every time you want to fetch any register from a different bank, you have to use this bank cell. Okay, so you use this instruction bank cell, and then select port A, which lies in the bank 0, and then clearing all the bits of port A. So we are clearing all the bits of port A, and then we have clear F port B. So we have, so port B lies in your bank 0, and that's why you do not have to select the bank again, and you're using the same bank, and then under that you're using this. So you're clearing F port B, and then clearing F tris A. So tris A basically sets all the bits in your port A as your output. So these two are interconnected. I could have also written this way, like tris A above this port B, then it could have been more clear that you have cleared the port A, and then you're making you're clearing the tris A also, and making and what does this instruction means? It means that you're setting all the bits in the port A as your output. Okay, and then this port B, you have cleared all the bits, and port B you'll be using because you remember you have RB4. RB4 is in your port B, and that RB4 we'll be using. Okay, so so clear F port B, and then coming to here, move LW, where L is your literal number, W is your working register. Move this literal number, which you see here, to the working register. Okay, so you're moving this literal number to the working register, and then move WF, which means move whatever you have in the working register into the file register. Okay, so tris B, you're moving this literal number into the tris B, which means your RB4 is going to be set, because you're providing this one. You remember this is RB0, RB1, RB2, RB3, RB4, RB5, 6, and 7. So RB4, you're setting RB4, and every time if you if in your tris, if you say, if you provide 1, or if you set any any 8-bit data in a trace, that means you're providing the input. Okay, so you have provided input to RB4 as input, set RB4 as input. Okay, so till now I hope you understand that you have moved this literal number into the trace B and setting the RB4 bit as your input. And what happens if you put 0 here? All these 8-bit numbers are 0. That means in that case your RB4 will be cleared and it will be act as a output in that case. But here you are just giving 1, so that's why it will act as an input. Now after these two steps we have call. So it's going to call init. Init is used for initialization. Initialize it again. So you'll go to this call init label. So there is some label defined in your program by this name. So we are going to jump into onto that label. So call init. Now we are going to jump here. So init is this label, and under this we have this program. And what does this program says? This program says move the literal number to the working register. Okay, and so this is our literal number. Okay, and we are moving this literal number to the file register. So move the literal number which you have moved into the working register from working register now to the file register. And what is the name of the file register? The file register name is LED_pattern. So you remember in the beginning we defined two general purpose register. One was flag_bit and then other was LED_pattern. So here comes the use of that general purpose register, and what we are trying to do is to move the value from the working register, this literal number, into this general purpose register. So when you do that, when you move this literal number into this general purpose register, then what will happen? Your RA4, which is your LED, your LED4, RA4 is your first LED from the right, that will be high. That's why you are using this, and it says then return. So once this is completed, it's going to return, which means it's going to return. But then we have a loop here, so it's going to go here. So it's going to follow this loop, and in this loop it says bit test f skip if set. Okay, so it's going to do the bit test, and your bit is the 4th bit. It's going to test the 4th bit, and always remember which port you are working on. You're working on port B. Okay, you are doing the bit test for port B. What is your port B? In port B, what you're using? In port B, you're using the switch, which is S1. Okay, so using the switch S1, port B, and you're testing the bit which is 4, and you remember RB4 is connected to switch 1, S1. Okay, so you're testing the bit at RB4, and what you're saying is what you see here is it is doing a bit test f skip if set. So if that bit is set, and you remember in the flowchart when it was set when the button was released. Okay, so when your button was released, at that time it was set. Okay, so if it is set, let's say if it is set, which means the button is released, then let's see what it says. If button is released or set, then skip the next instruction and go here. So it should skip this instruction and go here. Okay, so let's see. So case 1, when the button is released or set, in that case it will skip this instruction and will go to this BTFSC, and it's going to do again bit test on port B, and this time what it's going to see, it's going to see whether the button is pressed or not, or if it is pressed, then that means that fourth bit should be 0. Okay, so you know that when you press the button, then your RB4, the bit at RB4 bit is 0. So we have to assume a case right now to understand the program, and I'm assuming my case 1 says button is released, which means it is set. So at this point, when it reaches here, when it's asked this question whether the whether when you do the bit test for this particular bit RB4, so this fourth position, fourth is basically tells your position of the bit. So fourth position is your RB4 of this port B8 bit resistor, and it's checking whether it's 0 or not. So let's say it is set, it is not 0. Then what's going to happen? So if button is pressed or clear, then skip the next instruction. So I'm assuming my button is released, it is not cleared, it is set, then it is not going to skip the next instruction. There should be a T here, I'm missing a T. So it should not skip the next instruction, which means it should go to this instruction. So this instruction will not be skipped. It will be skipped only if the button is pressed. When it check this instruction set, if it says it is set, then it will go to this next instruction set. Okay, so in short, when your button is released or it is set, then these two steps it's going to do. So it's going to jump from here to here and check whether the button is pressed or it is clear. If it is still not clear, then it's going to go to this step, which means call LED_on. Now LED_on is my label. So it's going to go to this label. This is a subroutine. So it's going to go to this subroutine. So I'm going to, so this LED_on is label on next coming slide. So I'm going to click next to see what is there inside this label. So you remember what it is doing? It is I'm gonna quickly go here. So when it is the button is released or it is set, it was here and then went here and then went to the call. Okay, now next let's see. What if so before I go to the LED_on, let's see this second case when the button is pressed, and we are assuming that button is pressed and this is reset, or you can say clear. Okay, you see here when the button is pressed, it's clear. So you can write down instead of reset. If it is confusing, then you can write down here clear. So this is the second case. When the button is pressed, then what will happen? So it's going to do a bit test, whether test the bit, skip if set. So it is not set right now, so it is not going to skip this step. Okay, so it's going to go to this step called rotate_if if underscore needed. Okay, so it's going to go into oops, that was this quick. Okay, so you saw that it quickly came from this call to this call. So it will go to this call subroutine, and then will come back and then again test if the bit is clear or not. And if it is clear, then it's going to skip the step and go here, and if the bit is not clear, then it's going to go to this call LED_on. So now let's see what is this LED_on is and rotate if needed is. These are my two labels which I have used, and loop is also the label, and loop label you already see here is my loop label. And then I'm going to show you these two. Okay, so rotate if needed. I think I'll quickly go to first this one. I'll explain LED_on, And then I'll come back to, I'll explain then rotate if needed and rotate now, and then this. So right now we are just focusing on this one, and then next case would be explaining that part. Okay. So LED underscore on. So you remember in the flow chart I showed you when the LED is on, then we are using a flag bit, and in that flag bit the purpose of the flag bit is to clear the flag bit, and it was just using it, we used it as a status that LED is on, and we are clearing the flag bit. So that's what happening here. Starting here, move F, which means whatever you have in the working register is moved to the F. Okay, you remember what you have in the working register. If you go back here, so this was okay, so this was there in your working register. Okay, so moving this literal number into the LED pattern. So here, coming here, so you had 0 0 0 1 and then 0 0 0 in the working register, and which has moved to this LED underscore pattern, and then comma 0 0. This 0 indicates your D, which means where you want to store the data. If it is 0, that means you want to store the data into your working register. So LED pattern under comma 0, so data is stored in the working register, and from working register it has gone to the port A. So when that happens, as soon as it goes to the port A, the LED will be turned on. So in short, initially we sent a literal number to the LED underscore pattern general purpose register, and now here we are sending the literal number which was saved in the LED underscore pattern to the port A. And you know that in port A is you're connected to your RA4 and RA5, starting from RA0 to RA7, and RA4, RA5, RA6 and RA7 are our 4 LEDs. Okay, so it's going to turn on RA4 starting with RA4. Okay, and then it's going to do the it's going to clear the flag bit, and flag underscore bit is my another general purpose register. These are the two general purpose register. So this flag underscore bit comma 0, we use this with instruction set here, bit clear F. So what's going to do, it's going to clear the bit whichever we have mentioned here. So we have mentioned here 0th bit, so it's going to clear the 0 bit, okay, of this register. So this register is of 8-bit register, and it's going to check this 0th bit, and it's going to whatever is there at that bit, it's going to make it as 0 because you're using BCF. And if you have any confusion, just pause the video and see what this BCF mean. I've already explained in the instruction that that this is bit clear F, where you clear the bit, and that's why we have used here. And then now it says return. So wherever it has been called, you will basically return to that path. So let's see where it was called. So it was called here. Okay, so we have returned here and then go to loop. So loop will continue. Now let's see, we are going to see the subroutine for this subroutine, rotate if needed, call rotate if needed. So far we saw call LED underscore on, and now we are going to see rotate if needed. So here starts the code for rotate if needed. And in this one, if you remember on the flow chart, I showed you that we used the flag bit 2 times. One time we used when we wanted to turn on the LED when LED was on, and the other time I used when we are rotating the LED, right? So that's the another use, flag bit. So here, first of all, it is checking the 0th bit of the flag. So it is testing bit test F, skip if it is set. So it is testing the bit whether it is 0 or not. If a flag is set, skip the next instruction, don't rotate. Okay, if it is already set, if it is already 1, then it is not going to rotate the LED. It is going to go here. Okay, so let's assume that our flag bit is not set, it is 0. If it is 0, then it is going to go here, call rotate. So call rotate underscore now. So this rotate underscore now is again another subroutine. It's going to go here. So under subroutine, what does it say? It says RLF, which means rotate left. And you see here LED underscore pattern, in which we had this literal number, which was 0001 and then 0000. So it is going to rotate the bits in that 8-bit register towards left. Okay. Okay, so it says flag bit is made clear 0 every time the LED is turned on, and flag bit is made set every time LED is rotated. And that's what I explained you here. So when we are rotating, it is setting the flag bit at 0th place. Okay. And then, okay, so we saw that rotation has taken place using this instruction set. And then the next thing it says is the call adjust. One thing I want to let you all know that you see here one. What does it mean? If you see the instruction set for RLF, you'll get to know this basically stands for D, which means where you want to store the data. If you put 1, it means that you want to store the data in the file register. So we are trying to save the data into this LED underscore pattern register, and that's why we have made 1 here. And if you put 0, then it's going to store the data in the working register. Anyways, so now we're going to call this adjust subroutine. So going to the adjust subroutine, this is my adjust subroutine, and what I've done here is I'm doing the bit test F and skip if it is clear. Okay, so it is going to check the 0th bit of this LED pattern, which is the 8-bit resistor. The reason why it is doing it, it is going to check whether all the 4 LEDs have been rotated or not. Okay, and if it has or if all the 4 LEDs are rotated, then call init. What is this init? It is going to again feed the value into this resistor LED underscore pattern as 0001. So we're going to see that through this picture. So this is, you know, that what is happening. We are rotating the bits so that our LED can rotate, right? And this is my carry. This is my resistor F. And here you see the resistor in port A. So RA0, RA1, RA2, RA3 till RA7, and this is the carry, and that's how it looks like. So this is my literal number. Initially I placed in the working register, and from working register to the port A. And you know that RA4 is connected to the LED, RA5 is also connected, and RA6 and RA7 are connected to the LEDs. And our purpose is to rotate the LED towards left, which means with every button press, this should light up first, and then this should light up second every time I press the button. And then with the second button press, this should light up. With the third button press, this should light up, right? And with the fourth button press, this should light up again. So in a sequence. So this is what we have fed in the beginning, that 0001, 0000, and in carry we have 0. Now you see here, after one rotation towards left, this is going to happen. So this 0 is going to go into the carry, and this 0 will go into this RA0 position, because you see this is the 8-bit register starting from RA0 to RA7, and this is the carry. If you have 0 in carry here, then this 0 carry will go into RA0, and whatever you have in RA7 is going to go into this carry, and that's what it is happening here. You had 0 here in RA7 which is going into this carry, and this 0 in this carry is going into this RA0. And if you notice that your RA4 was 1 here, which means it was set and it has rotated towards left. And then the same thing is happening here. This 1 has been rotated here, and then rest these zeros are rotated towards here. And then again in the third cycle, this 1 has been rotated here and this 0 has been rotated here. And then in the fourth cycle, this 1 has been rotated here and whatever the 0 was here, rotated here. And in the fifth cycle, you see here, you got all zeros and this one has gone here. Now here comes the purpose of this bit test. Bit test F, skip if clear. So you see here, now you need to connect the dots. Okay, so the dots are, this RA0 is your this 0th bit, right? So what this instruction is set is testing. It is testing whether it is 0 or not. Okay, it is testing this bit every time. So if you see here, it says bit test F, skip if clear. So it's not going to initiate, it's not going to call this subroutine until it has all ones. So as soon as it has, all zeros. As soon as it has any one, then it's going to call this subroutine, which is INIT. So I hope it makes sense to you now that why did we use this bit test F, skip if it is clear. Okay, so it is going to skip this step and go to this return if it is all zeros, because that's what we want, right? We want bits to rotate, and it is bit rotating till here. But then at this point, when this bit is 1, then all of these are 0. That's what we know we don't want. We want it to sequentially rotate. Okay, so what happens when this bit is 1? Then what's going to go? It's going to call this subroutine, which is this INIT. And what was this INIT? If I move back to here in the beginning of the program, you see here, this was my INIT. And what did I do? Here I just moved this literal number to the working register, and from working register to the LED underscore pattern. Okay. So if you have any confusion, just pause the video and see each of these labels and try to connect the dots that how this program is working. Okay, now the next thing I'm going to show you, again the same slide which I showed you in the beginning, which is the full program. This is the full picture of the program here, and you see that this is our initial code. I'll just quickly read here: bank cell NCLP, clear F NCLP, bank cell port A, clear F port A, clear F port B, clear F tris A. Set all bits in port A as output, and then we are moving the literal number, this literal number, to tris B, because we want to set our RB4. RB4 is basically our switch S1, and then calling INIT. Now you must be looking at the INIT code. It's actually at the bottom. It doesn't matter wherever you place. It's a subroutine. You can call this subroutine anywhere. It doesn't have to be directly it shouldn't have to be in order. So your program actually, it just look for this INT in your code. So it sees here. And what does it say? It says transfer this literal number to this general purpose register. First to the working register, and from working register to this general purpose register, and then return. Okay, and then return, and then go to the loop. So go to this loop and ask this question again, whether the button is pressed or not. If it is not pressed, if the button is not released, if button is pressed, then it's going to go to this call rotate if needed subroutine, so which is here. Okay, and then it's going to do the bit test and skip if it is set. So flag bit, if it is set or not, it's going to test for that. If it is not set, then it's going to call rotate, and it will go here and rotate the LED towards left. And then it will call adjust, and then adjust will basically test the 0th bit, and then again call INT, and this will continue. So so this is basically the code for your rotating LED with input button. Now now your job is to run this code, exactly type out the same code which I have given here, and try to remove the lag in this code. Okay, try to remove the lag. You will see the lag when you upload it on your development board, and your job is to, first job is to remove that lag. Okay, remove that lag. And second, and there is an assignment I've already provided on Canvas, which says rotate the LED towards right, which means starting from RA7 to RA4. Okay, so that's your assignment. Rotate the LED towards right without any delay. So do that. So how to remove the lag? That's the question for you. Try to figure it out. What instruction set will be required to remove the lag? And this is the end of the lecture. Thank you so much for watching.